Hello, my name is Anton Antonov. I'm going to talk about conversational agents for neural networks, but more generally for machine learning workflows and algorithms. I'm using version 12 because I wanted to, for this conversational agents talk, I was thinking to hook up Alexa and show you stuff, but actually the speech recognized in version 12 is something I wanted to use. I still, unfortunately, doesn't parse my voice that well, but I hope I can, if we have time, I'm going to show you how it works. So what I'm trying to do is, that's why, because I'm using version 12, the pre-release, that's why it's not exactly the slideshow. It crashes. But I'm going to use the scrolling presentation, and to some extent I like it better. So what I'm trying to do is not to make a end user conversational agent for classification or whatever. I actually want to have a conversational agent that generates code, and this code we can take it and elaborate it further. So this is a conversational. I'm trying to design conversational agents that help data scientists, machine learning practitioners, or something, to generate code and utilize it further. So here, I think this should be live. So what's happening here, hopefully, because the talk's about neural network, I'm training some neural network, stopped it. But this here, what you see, is a monadic pipeline. So I'm going to elaborate further. I just want to give, in the first 2 minutes, very quick overview of what is the methodology. And presumably after that, you might decide you don't want to listen and go to another talk. So here what we see is interleaved code and comments. Roughly speaking, I'm going to show you how the comments, which are in between the executable code, they can be used as a conversational commands. And from these commands, we can generate the code. So there are several things here you might recognize. Actually, I'm not sure how useful this is, but this table here, it comes from the tracing. So this monadic pipeline here, which I generated, I just plug in this thing here to it. And this is my monadic pipeline symbol. And we can see a breakdown of the operations. So when this is executing, I'm going to execute it again. You're getting, increasingly, you're proclaiming some results are being proclaimed. It is a pipeline because we start with a certain data set. Here I wrap the data set into this tracing monad in order to produce this, to be able to make this comments and then to produce this table. But after I have trained the classifier, I want to see the measurements. I want to proclaim the measurements, what we see here. I want to see the receive operating characteristics, true positive versus false positive. I want to try to figure out what are the importance of the variables. We can see that passenger sex is most important for Titanic. And basically this is it. All right, so another executive summary type of thing. So I start with some data like this. And then, so this was classification. Now, if we do regression, actually, this is a little bit more interesting, probably. This is actually how this looks like, how this conversational agent looks like. So you can see that all of this, in some sense, this conversational agent or this methodology, it's like a single line interpreter. Each of these commands are being translated into something. This something, I'm going to demonstrate what it is. It's basically code. So if I pick any of those here, for example, this, I'm not sure what I did.
No, it's a copy-paste, but it's only the first time.
And what should I do now?
It's the mystery. Every time is different.
Damn. All right. Thank you. This was reassuring. So yeah, you can see with this, I generated new code. What is this new code? I mean, I said compute net regression with 20 epochs, and we can see the epochs and whatnot. So basically, if I can gather all these commands and produce code. I'm going to show you this later. Actually, this, by the way, it's a terrible fit from the What did I do? Okay. The plot here, which is supposed to be happening, it's made with, no, I deleted the whole thing. Oh, well, let me convince you. This is more interactive than I want it to be. But if I do it with 20 epochs, you can see what corresponds to the neural network. It's actually very poor. I can increase, say, the epochs. And this is going to compute it for a longer period. And now I'm going to get it better. Or I can say 2,000 epochs over, say, 4 seconds. And so presumably, this is going to train for 4 seconds and just going to produce the result. And you can see that now the curve, which corresponds to the neural network, it's better. So what is the big picture on this? So we start with some sort of problem domain, like, say, neural networks, classification, regression, what I was showing. Basically, I developed two domain-specific languages. One is a natural language, which is here on the left. And another one is a domain-specific language in Mathematica, or any other programming language. Then I try to, because they are both domain-specific languages, using certain formalism, namely monadic perspective, I can actually very easily map one to the other. What I was showing earlier with interleaved comments and code, it should be clear, but it does this correspondence. After I have done this for a while, presumably it gets more mature, I can start making different types of conversational agents. And what we see here is that first is the single line interpreter. I haven't went further than that. Then we can try to make a lookup of a series of commands and do some kind of optimization, like, say, what standard compilers do. And then you can hook it to some device like Alexa or Google Home, or whatever. All right. So the general workflow, what I'm describing here, is, it's pretty simple. In classification, we try to split the data. After we split the data, we train the classifiers, and then we try to evaluate what's going on. But look, this picture below, you can see that the whole thing is much more elaborated. There might be some assumptions about the data, for example. There might be some conditions. We might get wrong results or unsatisfactory results, like what I was doing earlier with quantile regression. And we can go through certain loop. So so it is much better. This is very difficult to support just with some options and some variations of one single command. It is much better to have a language for it. So what I usually do, I develop grammars, and these grammars, they're being verbalized, and being verbalized either in a programming language or natural language, and then we make the domain-specific languages corresponding to that. And further, after this is done, I proceed with making the conversational agents. So if you haven't seen what is a monad, well, you can see my presentation from last year, but you have seen it in one way or the other. Monads have been used in different type of mathematics. I apologize about this. Not sure what happened. Maybe I shouldn't have done it, but I wanted to make a live demo with something called DC. So something like this. So I guess some of you have figured out what this is. This is reverse Polish notation. What we're having here, we're having a function, free. This function, free, operates on a stack and puts the value 3 on that stack. Then we have a function for, which puts on top of the stack of the argument, which is a stack, a value 4. And we have a function multiply, which takes the top 2 elements of the stack and changes it into 1, and so forth. This P here, you're getting out of the monad. So basically, you're printing out the results. This is very similar to what we are going to see in when we use layers and so forth. This is not what I have. I'm sorry, this is the wrong presentation. So it's here. So when we train neural networks, for example, let me show you somewhere here below. I mean, this here, it's a clear invitation for this kind of specification. And I'm going to expand on this. Let's go further through the monad laws and whatnot. So, I mean, why is this important? If your code has certain algebraic structures in it, so your code has algebraic structure, you can actually manipulate this code in a certain way, like do code generation, do whatever I'm doing here. This is a very powerful technique, very useful. Few languages can utilize it. The guy who made Fortran, his name is John Bacchus. Bacchus-Nur formalism is what I use to do the grammars. So John Bacchus, for his Turing award, he wrote a paper, can we get away from the von Neumann architecture in programming or something? And so here I was actually advocating similar style, using putting algebraic properties in your programming code. Very few languages, as I said, can do it. Mathematica is one of them. So, I mean, if you look at this diagram here, it's fairly simple. What is happening? All this thing we saw before is just I can easily pull off with this binding and symbol matching and pattern matching in Mathematica. So this is what is happening. All right, so this is the single line command interpreter. As I mentioned, you can see some other stuff here. I mean, it's basically producing some other things. What is interesting here, okay, so if I have all of the commands, right? So I can produce this, this thing here, and then, well, not sure what exactly. Okay, so, all right, yeah. This is the important example which I was promising. So you can see this is what I showed earlier. This is how I translate a single line. But if I take this here, this is all of the commands I used. This is code which I can just take and plug into something like so DS Titanic, and then I put this code, and then I have the execution. So this is what is my goal. I want from this sequence of natural commands to produce code which I can later on modify in some way. So this is just for classification, but it's important to keep in mind that neural networks, they don't exist in a vacuum. So they need to be utilized in some way. And this is basically representing certain workflow, which you can see here from the natural commands. We're splitting the data, we're training an ensemble. That's actually an interesting thing here. I'm training an ensemble of classifiers, not just one classifier. And this is not something it's in Mathematica. But anyway, this workflow, which is actually fairly complicated, and it's not trivial to just do. So just training the neural network, it gives you some stuff, but you want to execute this kind of workflows as often as you want. And so one way to store workflows is actually to use this kind of specifications. As I said, this is a domain-specific language and concise enough to be used for other stuff. All right, so this here, it's not important. Let's look into, because this is about neural networks. Right now, I haven't plugged in the neural network classification, neural network objects into this classification monad. I did plug them in, though, into the quantile regression monad, which I was showing earlier. So with the quantile regression, it's somewhat easier because the data is simpler. And I'm not exactly sure what is the best way to proceed further with the management of the grammars and some other things. One of my goals is to actually discuss this. But now let's look into this, this command, which is about training a neural network chain. As I said, this is a clear monadic invitation here. All these elements here, we're transferring matrices from one to the other. That's why we have names like TensorFlow and whatnot. So this is a monadic pipeline. So I can even capitalize on this analogy, like say here with this, I made a simple parser. So you can see I have a parser which parses a layer, right? And this layer, and then I can extend it further in order to be able to parse more than one layer. And then actually, let me show you what is happening here. So if I do this, right? So I have this command, which I'm using the pipelining symbol between the layer elements. So I'm splitting here this command here. I'm splitting it to this pipeline, and I'm doing this. Now, what has happened? It just produced a list of layers. You'll say, so what? This was to begin with, But actually, here you see with this application command, this here is a shortcut of parse apply. So if I do something like this, I can actually make a parser, which basically produces a neural network. So what did I change? I just moved from, I just put parse apply. So this here now, all these strings which were parsed before, these strings of the layers, were turned into expression, and then I put name chain on it. And then using the fact that Mathematica can superimpose net chains. So if you do net chain of net chains, you produce a net chain. So we get this. As you can see, we do have some algebraic structures in the code. So Wolfram Research, they have done a very good job. They have implemented a monad for doing neural network chain training. And not training, just specification and training. So in some sense, this is the big message here. So now here, like if you look at the command, here it's like, would be nice to be able to do some complicated commands like this, like, an element-wise layer, then with 10, then convolutional layer, and so forth, right? So, and further, we might want to do other commands. I have listed some. I haven't implemented all of these. Some of them were like wishful thinking, but this actually here, it's interesting. I haven't done this yet, but I have done the grammars. I haven't done the implementations. Most of the time, you're not training new neural networks. You're just retrieving an existing network from some repository, like say the Wolfram repository, and then you're modifying it slightly, and then you're plugging it in your big flow, like say the classification workflows I showed, or the quantile regression workflows I showed. So this is what I'm currently working on. So here, this slide or this is just going through different. I mean, just evaluate it here, I guess. It's just showing how I parse different commands. Like if you say list models, this is a net repository query, blah, blah. Now, what is happening here is that because Mathematica is homoiconic, meaning Mathematica can interpret its own code, this means that you can actually very easily hook up to the abstract syntax trees which come from the parsers via Mathematica code. I just need to provide some implementation behind these functions. And I'm going to have a functional, not just parser, I'm going to have a functional interpreter. You can see some of the other things I have done here. The interpreter itself, actually, before going to the interpreter, it's useful to generate, when you have these grammars, to kind of have an overview of some sort of what is going on, right? And you can see here with this, I'm generating 20 random sentences with the neural network monad, and you can see one of the commands it can understand. I mean, some of these are not particularly impressive, but like something we saw earlier. Train neural network for whatever number of epochs, whatever batches, and so forth, right? I mean, this here is repetitive because if you look at the options of net train, I mean, there is no point for me, there is no order between these. I need to be able to handle all of this. So I can just have, I just have any kind of combination, any kind of list of possible candidates here can be used. So that's why, for example, we see the repetition of this of batch size. All right. Well, I mean, similar for this classification monad. It's like, you know, you can see all these commands were being for the classification monad. All these commands are interpreted. They're not just parsed, they're interpreted. I was showing this earlier when I was running stuff. So, I mean, you can put more complicated commands or try to consider if you have a list of commands, like can you do something better, not just interpret them one by one, but can you actually, if you know all of the commands which are being given, can you do something better? This here is what I was saying. What the interpreter is fairly easy to do. If you look at these pieces of code which happen from the neural network monad commands, I'm basically just hooking up some simple implementations, very really simple implementations of this. And here, when I run this is how I get. I guess I didn't do it. All right, let me run it here and see what's going to happen. This is not well. Unfortunately, this is something I didn't implement yet. The decoders and the decoders. I'm going to run the net chains, and so you see this PRS is having mathematical expressions for the net chains, and you can see now this PRS without the interpretation, right? It's just a bunch of abstract syntax trees which happen to be code. But if I put appropriate implementations to the hooks which are represented here, I'm going to get these neural networks, and then I can need to train them and do other stuff. So ideally, I want to do something like this for the neural network monad. I'm not sure that this is the best way actually to do it, because you see, for example, here, this is how I actually, if I make a full-blown conversational agent, for example, the user doesn't need to type this anyway. But so what is happening here, I'm having interpret a command for the quantile regression monad. And if I want to train to attach a new neural network, so if I look at this is something we have seen before, right? So this is just this is a pipeline for the neural network monad. But this pipeline, with this overriding here in block, I can turn it into a quantile regression pipeline. And in this quantile regression pipeline, I can actually utilize it to train the expressions and proceed further. All right, so what is happening here is that at this point, the neural network conversational agent, it's not high in my priority to make it convenient to construct new neural networks. I want to make it convenient to be used in larger kind of workflows, like workflows which are outside of the neural networks. I'm not saying I'm not going to do it. It's just not, I don't see it as high priority as being able to retrieve neural networks from a repository, being able to search them. This is the sparse matrix recommender monad on top, which I didn't demonstrate here. And after you have the monad, after you have the net chain or net graph, you actually can put it in the classification monad, the CL-con at the bottom, and then you can, produce, work with your workflows. There's some, and this here is an example of how we can do, and I need to finish here. And so basically, this here, this is just for a phone book, right? Like I have a phone book with professions, the occupations and the companies of different type of employees. And I can say the third one. And so with the third one, we're going to pick particular person and and so forth. And then if I say something like say call live, I mean immediately finds a particular person and calls them. So anyway, this thing here can be done for the repository of the neural networks. it is very important when you develop this kind of functionalities to have a lot of unit tests. These pipelines, they need to be designed to fail. So I basically have two types of unit tests, one handmade, man-made, the other one is randomly generated. I generate, like, say, 1,000 pipelines, and then I see, do I have any failure? If there is a failure, I try to address it. This, by the way, is extremely important because especially if you're making a conversational agent, especially if it's connected to some device like Alexa, you need to be able to follow gracefully. All right, so you can see some of my future plans here. So one of the usual questions when I discuss this approach is that, yeah, but why are you doing this by hand? Why you cannot do this stochastically? Cannot do it with whatever, like the speech neural networks people represented? Well, I really don't see how they can train automatically from a book or from a body of text a conversational agent or any kind of, anything that can generate programming code, meaningful programming code from specifications, like natural language specifications. So my approach to this is I usually program the initial grammars, like what I showed here, and then I try to extend them, try to make them fuzzier. I mean, obviously, you should be able to handle certain mispronunciations, misspellings, and etc. This actually can be done fairly nicely. This analogy with the Terminator, the Terminators in the different movies, it's apt because you start with the rigid skeleton, then you have just the liquid, Terminator, but actually the best one was liquid metal over rigid skeleton method, which is by Christian Loken in the Terminator X or whatever. Neural network graphs, there's several implementations for this to be used, but I want to use it from a more general perspective. I'm nearly out of time, so you can look at the references here. And basically, my big push for this conference and this talk was to actually make this pipeline work. And so, and which actually doesn't, for whatever reasons, because I overrode the implementations when I was demonstrating the expressions. But this here, it's the current stage where I'm at, and I plan to expand it further to work with classifiers, with the classification workflows, not just the regression workflow, which is here, and to be able to retrieve data from repositories. Thank you for your attention, and if you have questions.